Hi everyone, so happy to see you all here again to today's episode. And I welcome Wojtek, welcome you.
Hey Stefan, how are you?
Thanks for joining us today. Where are you based?
I'm actually based in Lisbon in Portugal, although originally I'm from Poland.
Come on, in Lisbon, Portugal. So in Lisbon at the moment? Wow.
Life is good here.
Is it hot?
It's not that hot, it's like 27, so it's perfect.
Oh, that's fine, that sounds good. I love Lisbon. I went there for holidays at one point, but it was years ago and it was so beautiful, the seaside.
Yeah. It is a very nice city, and yeah, it's also a great destination for people who like surfing. I've been getting into that recently.
So you're a surfer as well?
Not much yet, but you know, getting started.
About to get there. Okay. Anyway, it's also good for startups, right? Because Web Summit is taking place in Lisbon, so it's perfect to stay there to get in touch with investors, right?
Definitely, it is a tech hub. It has like 5 unicorns now and a lot of startups. I would say the capital markets are not really developed there yet, but that's changing.
Yeah. Okay. I could imagine that the infrastructure is beautiful and it's just nice to live there for some reason. So I think that's awesome. So I know someone from Lisbon now. That's cool. So Wojtek, you're a founder of a company which is called NannyML. What are you doing? So what is your background?
Yeah, so my background is in mechanical engineering and then artificial intelligence. So I'm really a techie, like, you know, data science, not even that much of an engineer, but really a data scientist from like research perspective. And NannyML is an open source library for detecting silent model failure. So what I mean by that is you deploy a model in production, a machine learning model, and you want to make sure that this model keeps on operating. And sometimes you don't even know whether this model is working well or not. And NannyML is a library that allows you to basically detect if your performance goes down and figure out why. It's open source, built in Python, all that cool stuff.
This is the thing I was fascinated with. So yeah, when I just read it, that it's open source, which is cool, right? I can tell you that this community loves open source. So when you decided to build an open source model and open source software, what drove you? Have you been frustrated with ML modeling, or what was the reason why?
So like actually NannyML was born out of like a real need. I used to run an end-to-end machine learning consultancy before, and we developed projects from like, you know, from the business use case to actually putting in production.
Yeah.
And then our clients were asking always like, okay, this is good, but how do I make sure it keeps on working?
Yeah.
And we're saying it's not our problem. It's delivered and it's way too much work to manually maintain it and monitor it. But then we started to see a pattern and we said, if we make it our problem, we can actually make a product that's very useful for a lot of people and can bring a lot of value.
Yeah.
And that's really the story.
Cool. That's awesome. So the kind of open source I love because it's something which is easy to show and everyone can experiment with it, which is beautiful, right?
Absolutely. And I noticed also data scientists really love open source, and it doesn't make sense to build something that's closed source in this day and age. It just will not get any adoption. And it's so much harder to develop if you're not developing in public, because the iteration takes much longer. If you want to get feedback, you need to show something that's not open. Now we can just tell people, you know, just install it, let me know how it works. And it's much easier to use it, but also to be behind it.
Absolutely, yeah, sure. I mean, what's beautiful about it is that you have can really build a community around it, which is a completely different thing. I like that. So welcome everyone who just joined. Happy to welcome you today to today's episode with Wojtek, who is going to talk more about the model we built, the open source code, and just a few remarks regarding the organization of it. You see the navigation bar, which should be attached to Zoom webinar here. There's a Q&A section where you can actually ask questions. So please feel free and feel invited to ask any questions you have during the presentation. It's my job and I will have a look at it, but you get your answers. And Wojtek, I know he's keen to answer questions because, yeah, he's the community guy. So anyway, he's interested in answering your questions. So
absolutely.
yeah, I'm really excited about it because how old is the startup, by the way?
About a year and a half, closer to like a year and 4 months. So proper startup.
Cool. So it's not just a baby, it's already running, right? It's walking.
Walking. I wouldn't say running, but walking. Yes, we're walking.
Okay, so we're getting into an exciting phase now. Have you been the solo founder or you as a team?
So we are a team. So there's 3 founders. I'm one of the co-founders, and we are in total right now, I believe, 12 people.
Oh, cool.
Across, data science, engineering, and now also recently, very small growth team.
Are you looking for people as well?
Yes, actually, that is a very good point, and that is a perfect audience. We just started hiring for data science interns. We're looking for 3 interns in data science to help us, develop the algorithm, test it, validate it, make sure that our algorithms to detect drop in performance and estimate performance work well. So if you're in your stage in your career when you're looking for internships, absolutely do apply. You will see my LinkedIn at the end of the presentation. You can just go there and there will be a post about it.
That sounds good. So I'm now more than curious to understand what kind of internship you get when you apply with you. So please show me. Take the floor, please.
That is something that we are just publishing today. Like, actually, I did not plan to do any advertisement of that. So
okay.
Maybe I can walk you through it at the end of the presentation. There's a bit of time. It should be online by then, but we'll see.
Yeah. Okay.
Cool. So is it okay if I start screen sharing and jump right to it? Okay, cool.
Completely excited. Yeah.
All right. So today we're going to talk about detecting silent machine learning failure. So it can serve as a kind of an introduction to how you should be doing machine learning monitoring in your models after you deploy them in production. We're going to focus much more on high-level concept and kind of intuition behind things. We define kind of the main things to focus on, and we'll leave the details and all that kind of stuff for later. So on the agenda, first, we're going to cover 2 main reasons why the models can fail in production, and this is the data drift and concept drift. We'll define them, and we'll define how they can actually contribute to model failure and what can we do to detect them, and then take them into account when fixing our models. Then we're going to talk about the kind of core of machine learning monitoring, which is performance estimation, and we'll see why it's needed, and we cannot just calculate performance. And then at the end, we're going to go back to data drift and concept drift, and we're going to talk about how to detect those in order to find the potential underlying causes of drop in performance and go from identifying that there's a problem to fixing it. So that's on the agenda, and we're going to set the stage with a very simple typical use case that I'm going to refer to throughout the presentation, and it's going to be a use case about a loan default prediction. So we're going to the realm of finance, and imagine that you have some credit score, some customer information, and you are trying to predict whether a given customer is going to pay back their loan or not. We're going to define a target from business perspective as a non-payment within a year, which means we'll have to wait an entire year to know whether the prediction was correct or not. And as always, we need to find a technical metric to evaluate the quality of our model, and for that we can use ROC AUC, which is a very typical metric when evaluating binary classification models. So let's get started with the causes, so the data drift and concept drift. And to do that, we need to first define what are we trying to actually do when we train a machine learning model. So what happens is there is some kind of pattern in reality, some unknown pattern that we're trying to capture between the model inputs and the target. So imagine that you have just one feature, feature X, and as this feature X increases, it is more likely that the given data point is going to be, belong to a negative class. It's a hidden pattern in the data. It exists out in the world. Then we're going to get some kind of sample of this pattern of this population in our data, in our training data, and we will see that this same pattern is visible in our data set, and this is going to be the data that we train our model, evaluate, and test our model. So these are the basics. That's kind of how machine learning works. And now let's talk about what happens if we see data drift. So data drift can be defined as change in kind of the sampling method. So the true pattern that we're still trying to find, it will not change. It's still going to be the same pattern. Here we see that as x increases, then in this kind of sigmoidal-ish shape, we will see that it's more and more likely that you have a negative class. But what will change is how we sample this data. So imagine that previously we sampled how you see in the original sample here, and our new sample is shifted a bit to the right. That means that our new data will have the same pattern, but will look very differently. And that can, but doesn't have to lead to model failure. Yes, Stefan.
Oh, fine. I'm just curious to see.
Okay. And so you can see it here as kind of a summary, is that it's a change in joint model distribution, to use a technical term. So you'll see that all joint distribution of all the model inputs is changing. And if this change is from a region when the model is performing very well to another region when the model is performing equally well, we don't expect to see drop in performance. But maybe the data is going to live from regions that were maybe far away from the class boundary to regions that are very close to the class boundary. And that will mean that we expect to see a drop in performance. More on that later. Now, let's talk about the concept drift. So concept drift, unlike data drift, is a change in the true pattern that we are actually trying to learn. So this true pattern that we learned in our training data set is no longer valid. It's slightly different now. Here is this example. You see that the growth in chance that the data point belongs to a negative class is not as fast as it used to be before. So we see slight change in the concept. And in pure concept drift, if there is no data drift at the same time, we will sample our data in exactly the same way, one-to-one, the same thing, but our data will have different class distribution. And that almost always leads to model failure because the pattern that was captured by the model is no longer valid. So the model will have a false or outdated vision of reality. And we can define it a bit more theoretically or a bit formally as change in the underlying concept between the target and model input. So the probability of the target given the input data, so given X. And we see, for example, here that could be visualized as change in the class boundary, that you have a training data that's distributed in some way, and then you see very similar distribution in production data, but the class boundary is going to look completely different. And that, of course, means that these 3 points here would be misclassified because they are trained to be in positive class, but they are actually now in negative class. So these are 2 main reasons why machine learning models can fail. And now let's move to the second part, which is why should we really focus less on these reasons and more on the thing that really drives the business, which is performance. So first reason is you might think that you can just monitor data drift, and then if something happens there, it means we need to investigate. And that would be true in an ideal world if you had infinite manpower to do it, but data will drift constantly, but only very small chance, a very small percentage of data drifting will actually lead to drop in performance. So just detecting data drift will actually not inform very well about the quality of your model. That's one thing. Another reason why we really need to care about performance is that it's something that we explicitly optimize for in training. So it only makes sense that we continue to care about it after we deploy it in production and not just forget about it. And then the last reason, which is kind of the most obvious reason, is that we choose the performance metrics such as log AUC or precision or recall or accuracy, or in regression, other metrics, of course, because it is a proxy for the business impact. And as long as we work, in industry and we develop real-world machine learning applications, we want them to be useful. We want them to bring some kind of value, and we measure this value by measuring the performance of machine learning algorithms. So we need to just care about it, as simple as that. And so ideally, we would look at our predictions, compare them to ground truth or to target data, and just measure performance, just like we did when we evaluated our model on test set. But the thing is that in production, this is not possible, or it's very rarely possible. First, let's look at our example use case. And there we need to wait entire year before we really knew what's going on and whether our models are working well or not. So this is not possible to just calculate the data. We need to do something more here. Second thing is that the labels are very often incomplete. What I mean by incomplete labels is that here, and again, let's take our use case, and we will always know whether the person that we gave the loan to has defaulted or not. But we won't know what would have happened if we gave the loan to the people that did not receive the loan, whether they would have defaulted or not. So the people that we rejected, we have no information about them. We don't know whether the negatives are true negatives or false negatives. So our labels are not complete. We only get kind of half of the confusion matrix. And then the third reason why we rarely have access to ground truth is a kind of family of use cases that are called automation use cases. And these are all the use cases when we're trying to replace humans doing some menial boring task, like document classification. Then the entire point of the use case is to stop humans from verifying every single prediction of the model, because that would defeat the purpose of the model. And sure, you can do spot checks. You can maybe verify and double check 1% of the use of the data points, maybe 5%. But for vast majority of the data, you will not have the ground truth. So it won't be possible to just calculate the performance. And that's why we need to estimate performance. And here I'm going to give you just very high level intuition behind how the performance algorithm that we developed works. So what we're doing is that we're going to train the model, and we're going to look at the confidence of the model. And the way we approach the confidence is we look at model scores. So when you do classification model, you get the model predictions, but also model scores, something that in scikit-learn you'd get from predict proba. And those can be interpreted as probabilities if they fulfill the definition of a probability, which is in a given sample, if you have a lot of numbers that say 0.5, then 50% of those should turn into positive and 50% of those should turn into negative class. And not all model scores are probabilities, but you can calibrate them to turn them into probabilities. I will skip this part because it's known science. It's something that that has been done multiple times. So we just need to make sure that we are working with calibrated probabilities. Once we have those, we can link the confidence of a model to actual performance. Imagine that you have a lot of points that are in these dark green areas here where the model is very confident. These areas, these kind of wings of a butterfly, we know that these are maybe areas that correspond to high density of class 1 and class 0, and they are far away from the class boundary. We would expect the model to perform there very well, and we can kind of compute the expected performance based on these probabilities. Now imagine that you see data drift closer to the class boundary. So the picture on the left here, on the right here. Then you would see that model is going to be on average much less certain about its predictions, because there's a lot of predictions that really fall close to the border. That means that we would expect the model to perform worse. And we can quantify it using reasonably simple math that I will link to later on. And based on that, you can see what is the expected performance of your model. And as long as there is just data drift and no concept drift, this estimation will actually be almost perfectly accurate, which is good news because it means that we can still see how well our models are performing even without having the ground truth. Just to give you an example here, we created a very simple example using California housing dataset, which is something that most of you, especially the younger data scientists among you, are quite familiar with. It's a dataset that's available almost everywhere, typical toy dataset, where you're trying to basically see what is the price of a house in California. What we did is we binarized, so we're trying to predict whether a house is going to be above or below the median value in the dataset. So we turned it into a classification problem. We trained a model. I believe we trained a random forest here, and then we estimated the performance. And what you will see in this dataset is that there's actually strong data drift, as houses later in the dataset tend to be more south, and the structure of the market is different there. And you see that the performance of the model will change significantly, and we can capture that using the algorithm that I've outlined above. So you see that it can work if there is strong data drift component. when it comes to performance. And now we go to the third part of our presentation, which is the data drift detection. So here what we're trying to do is we're trying to detect potential reasons for the drop in performance. We already have this algorithm that kind of magically says what is the expected performance. Now we're trying to figure out why, what has changed in the data so that we see a change in performance. And we can do it in two different ways. The first one is the univariate way. So we will look at every feature by feature separately. We'll look at them as independent features, and we'll try to see how these features evolve over time. And to do that, we can use statistical tests like KS test or chi-square test that basically measures the difference between two distributions. And one really good thing about looking at it from this perspective is that they are very interpretable. You can literally understand that a certain feature just changed. However, they have a few shortcomings. One of the most important ones is that if you have a data set with, say, 200 features, which is absolutely common in more advanced machine learning use cases, you will get really a lot of false positives and you'll just drown in alerts. There will be nothing there that you can use because there's too much alerts thrown at you. So a lot of them will be false. Even if they are statistically significant, they will not be significant from monitoring perspective. Is that there is a chance, but the model is robust enough to actually deal with it. And another significant shortcoming is that they treat all the features as independent implicitly. And if there is a change, not in univariate distribution, but there is change maybe in correlation between features, these tests will completely fail to see that. So basically to figure that, address that shortcoming, we came up with another way of looking at multivariate data drift. And here we developed a method when you can take the original data, compress it in some way, or embed it in some way, and then reconstruct it. And then we will measure the change between the original and the reconstructed data. The easiest algorithm to visualize that with is variational autoencoder. When we're trying to compress the data in the latent space, the algorithm learns the structure of the data during the compression. And we're going to train this autoencoder on our reference data set. Maybe it's a testing data set for which we know that everything is fine. We'll take this trained autoencoder, and then we're going to run data through it after the model has been deployed. And if we see that there is an increase in reconstruction error, so the difference between the dislocation of points before and after the reconstruction, that means that there is data drift, and this data drift can be in any way. It can be nonlinear change in correlation, can be really anything, and this algorithm will pick it up. The reason being that the internal structure of the data that has been learned on our reference data set has changed, and it's no longer a good encoding of the data. And I mentioned that we could use a variational autoencoder, but we could also use anything else here, even PCA. And there's only a few requirements for this underlying algorithm to make it work. First, the encoding needs to learn the internal structure of the data. Then the encoding needs to reduce dimensionality of the data. So there needs to be some kind of compression there. We need to be able to make an inverse transformation to calculate this reconstruction error. And there is one that's kind of slightly less obvious requirement, which is the latent structure. The structure after compression needs to map in a stable way to original space. And imagine now taking an autoencoder that is not variational. There, as some of you might know, the mapping from the latent space to the original space is very, very uncertain. So even a small change in the latent space can lead to a huge change in the original space, which means that our reconstruction error wouldn't really be feasible. So just give me a second.
Yeah, we have a construction site outside, right? But it's
yes,
it's fine. It was not disturbing, so it was only a little. That's fine.
Yeah, sorry for that. It should be okay now. So yeah, basically that's what we do. Then we're gonna measure this reconstruction error by using any metric. You can just use the mean of Euclidean distance. That's what we're using internally, and you get a reconstruction error, which is the measure of this dislocation. If it increases over time, there's data drift. If it stays the same, there's no data drift. And interestingly enough, if it decreases, you also have data drift. And let me explain here. The encoding learns the internal structure of the data, but it doesn't learn it perfect. There's some regularization, some things like that. If you see that the reconstruction decreases over time, that means that the learned structure of the data is actually it's closer to the real structure of the data now than it was before, which means that the structure of the data still has changed, just in a kind of opposite direction. So it became simpler. And then we can use that to recapture in one number all kinds of data drift, which means that we don't really have that much false positives, but we are, on the other hand, also sacrificing a bit of interpretability because we don't really know what kind of drift really happened there, and we need to dig deeper. But we can run it on subset of the data to recover some of the interpretability. And just to give you an example of why this kind of multivariate reconstruction approach is needed, take a look at this data set here. When the data points in blue are the reference data set for which we know the performance of the data, and the data points in orange are the analysis data set for which we don't know the structure of the data. We want to see whether there's some data drift or not. And if we look at univariate data drift results along the X and Y axis, we will see that everything's the same because the distributions actually look the same. However, if you look at it using our reconstruction error method, you will see a very strong spike in reconstruction error because the actual structure of the data has significantly changed. And we are now nearing the end of the presentation. So let's summarize. First, the data drift does not always lead to drop in performance, whereas concept drift, which is the second important reason why the performance can drop, is almost always a reason for failure. Secondly, the production targets are often not available to calculate performance, and calculating performance or getting performance is really the only thing that matters, because that's what you want to optimize when you monitor your models and when you develop your models. So performance estimation without the target data is key to ML monitoring, and you really need to do it in order to have a kind of holistic and full view of what's going on in your models that you can rely on and then you can act on. And that's it. So thanks for listening. And as I already mentioned, and so did Stefan, check out our GitHub. And we're an open source library. If you like it, give us a star. We're still a very small company, and very small library, and every bit of visibility helps. Also, feel free to check the website to see a bit more about the library from slightly less technical perspective. And also do add me on LinkedIn. I post updates there, also including everything that has to do with recruitment. So if you add me on LinkedIn, you'll definitely see any open positions we might have. And that's it. Thank you very much.
Thank you, Wojtek. I posted some of the links you mentioned for anyone who would like to know more, dig deeper into what NannyML is doing, so the website. Also, I sent the link to your actually LinkedIn page, right? Which shows that beautiful picture of Lisbon, which is awesome.
It does. It does.
But if you can switch for a second to the GitHub repository. I don't know if you have it in the background.
Sure, just give me a second. I will stop sharing. And
I can share my screen for a second until you have it. So
here I have it also on my side now.
Can you share it?
Yep.
So for any, you prefer black. That's nice. Okay.
I prefer black. Yes.
No mode. Okay, cool. Yes, for anyone who would like to know a little more. So this is the repository of for the download. Anything we should know when we want to start, when we want to know how it works. Well, where would you actually start with?
Yeah, so I think README is a good place to start, just to read about it, what it is. But given that now you should have a kind of an idea of what's going on, just go to the first thing, which is the documentation. Check out documentation, go to Quick Start. In the Quick Start, you can just literally copy paste this code, see what happens. You'll get some results. And that is the perfect way to start for the kind of people that just want to run the code. I'm one of those. But there is, of course, another kind of archetype of a data scientist who wants to know how things work before they start working on things. And for that, you go to how it works. And you can, for example, take a look at our magic sauce, which is this performance estimation. And here you will see how things work from mathematical perspective. If you're more a visual person, our launch got picked up by a few bloggers, and I actually have one of their blogs here. I am also happy to share it. And he wrote about how to do it. It was apparently very interesting. And you can see very nice explanation. On Medium, there's actually 2 blogs that I found that are quite interesting. And he gives a very interesting visual explanation of how our algorithm works. So give it a try. There's another one also on Medium, estimating performance without ground truth. So basically, these are the places to go to. Start with GitHub, go to docs. Our website is also there, but for me, actually, GitHub is a better way to learn about stuff because you have the code there and you have in-depth documentation.
Awesome. So how does the community connect? I saw you have a Slack page as well, right?
Yeah, let me go to GitHub again. And you can just go here. If you click on this community Slack, you will receive an invitation to our Slack. There's, I think, around 150 people right now there. We're slowly getting started. It's not a big community, but things are happening.
And you're number 3 of Product Hunt, Product of the Day. Wow.
Yes, we are. Thank you.
Okay, nice one. Okay, so we have everything in place, basically starting from GitHub as a main source, right?
Yeah, I would really go with GitHub.
Yeah.
You know, bookmark it and yeah, get started.
So I hope you guys get excited and just give it a try. I think it's worth it. And maybe we can revisit you next year again to see how you made progress, where you are at that stage. And yeah, thanks again for joining us and explaining everything to us. The video of the session will be recorded, as you've seen, so we were going to share it within the next days. So if you say, oh, I need to go back and try to remember what Wojtek said, now the presentation will be up there for download. So thanks again, Wojtek, for taking the time to show you everything.
Yeah, and I just see that actually one of the people from NannyML, Adam, just sent here a link in chat to the data science intern application. So feel free to check it out. It's already online.
I can send it to the community as well. So I think it's fine to know what there's the opportunities. Do you have to be in Lisbon for the intern?
Oh, no, actually, that's something. It's great that you mentioned that. We hire across Europe and actually across European time zones. So even if you're not in Europe, also feel free to apply. We are a fully remote company. The only requirement is for you to be able to travel freely across European Union because we meet from time to time. It's good to see each other in person every quarter or so. But apart from that, wherever you are, feel free to apply. And yeah, hopefully we'll talk soon.
Good luck with your journey. I wish you all the best with NannyML. Thanks again, Wojtek, and thanks.
Thanks so much, Stefan. And likewise.
Have a nice evening then.
Yeah.
Bye-bye.
Bye.